if my odds ratio for my continuous predictor is 1.5, and I say a 5-point increase is some sort of meaningful unit, what I would do is take 1.5, take that to the 5th power, and then I've got close to a 660% increase in the odds of falling, given a 5-unit increase in sort of whatever my predictor is here. Okay. Same thing, odds ratio is less than 1. This indicates a reduction in the odds or decreased likelihood. So for example, we've got an odds ratio of 0.8. We'd say the likelihood, and so you want to be careful as you're interpreting this, right? So you would say the likelihood is 0.8 times that of a non-event given a unit increase in your predictor. What you don't want to say is the likelihood is 0.8, represent a 0.8 times a decrease, because it's already an odds ratio less than 1, right? So if you're just talking about it, you're just saying the odds of falling versus not falling are 0.8 times, or the likelihood of falling is 0.8 times that of not falling, given a sort of switch from autumn to spring. Right? You don't have to say a decrease because it's an odds ratio less than 1. It already says that. Now, if you want to talk about things in decreasing terms, again, what we can do is we can take 1 minus this 0.8, and we can say alternatively our odds of falling are decreased by 20% by skiing in the autumn versus the spring. Okay, but same thing here. If this was if this odds ratio corresponded to some continuous predictor, right, and we wanted to see what a 5-unit change would correspond to, take 0.8 to the 5th power, right, and then we're going to say, and then whatever that odds ratio is, subtract that from 1, or take that away from 1, and so we'd end up saying that we've got a 5-unit increase results in the 67.2% decrease in the odds. Okay, so this is where people get tripped up. If you're talking about this odds ratio and just interpret it as a likelihood, you don't have to say increase, decrease. You just say the odds of an event are 0.8 times that of a non-event, given a unit increase in here. Because you've already, so the fact that you're reporting an odds ratio that's a decimal already indicates that it's a decrease to anybody who's sort of knows what they're looking at, right? But if you wanted to say and really emphasize that, no, this is a decrease in the likelihood of this happening, what we can do is then talk about this as a percentage decrease, right? So if we're talking about odds ratios in terms of likelihood, we're not talking about an increase or decrease in likelihood of odds. We just say what the odds are. But if we want to talk about it in terms of increasing, decreasing, we can take that odds ratio, subtract 1, and then interpret it as percentage. Yeah?
So going up to where we're talking about the odds of falling.
Yeah.
So when it says the odds ratio indicates that holding other predictors constant at 0.
Yeah.
What would, in this example, what would that mean with autumn, winter, and spring? Since spring is my reference, is holding things constant talking about just for spring?
Beautiful. Absolutely fantastic. Yeah, absolutely right. No. This is exactly what you should be doing. Like, think about, like, what does it mean when everything else is held constant at 0, right? Now, remember, these are additive models. So really, when we're talking about everything held constant at 0, we're just saying that once we account for these other variables, this is a unique prediction of this outcome, or this predictor for our outcome, right? Because we wouldn't expect, even if we were to talk about for difficulty, I'm assuming that difficulty, the impact of difficulty is independent of what season it is, right? So I would expect the odds of falling to increase at the same rate regardless of whether or not it's spring, autumn, or winter, right? What would we need to do if we thought that the odds of falling may change based on the impact of slope difficulty on the odds of falling? If we thought that would change depending on when we're talking about spring, autumn, or fall, what would we need to do? Judah. If we think that the relation between one predictor and our outcome is going to change based on another predictor, what do we need to do to model that?
Put it in the model.
What do we need to do special to it, though? Anybody have an idea?
It needs to be a
exactly, right? And so what does that mean?
So you need to multiply it by whatever you're expecting to change.
Right, and so what do we call that? An interaction, right? There we go, absolutely right. If we think, so we're saying, and you guys are fantastic, so absolutely right. We're talking about specifically, if we're getting down to the nitty-gritty, what this is doing is it's estimating the impact of trail difficulty on the odds ratio of falling for people who are skiing in spring, because that's our reference group. That's what it means when everything else is held constant at 0, right? But technically, within these models, we're assuming a constant relation across all other variables, right? Because it's an additive model. If we think that, and this isn't, if people, anybody ski? No, there are no skiers here. But it wouldn't be unreasonable to think that, depending on the season, that people may be more likely to fall in crappy spring snow or something like that relative to another, right? And so, but if we thought that that's was something that would go on, we would need to create an interaction term, right? So then we would need to have an interaction of season and trail difficulty. We'd actually end up with 2 interaction terms in there, right? One for our first indicator, one for our second indicator to model that. But you're absolutely right. This is saying that this is the odds of, represents holding everything else constant at 0, the odds of falling versus not falling per unit increase in, for a 1 unit change in trail difficulty. Now, again, the assumption is that sort of increasing the odds of falling is going to be constant, just given the way we've set up our model. But we can change this model to start getting more interesting types of effects there. Yeah.
So to explain that, whenever you held constant at 0, you can technically write during the spring.
Yeah, yeah. I mean, and that's how you would interpret the the intercept, right, for this model, right? What are the odds of falling for people if we, okay, so how would, if we code trail difficulty 0, 1, 2, and we have our 2 indicators for season, what do we how do we interpret the intercept?
Constant, 0.
Right. And so, but what's the literal interpretation of that constant?
That's just your likelihood of falling?
The odds of falling if what?
If it's not the other 2 seasons.
Which would be?
What is it, autumn and spring? No, autumn and
Winter.
winter.
Okay. So the odds of falling in spring for, what's our other predictor?
Trail difficulty.
And if trail difficulty is, if 0 is easy, right? Our intercept is going to be the odds of falling for an individual skiing on an easy trail in the spring. See what I mean? Okay, and so this is where, and this isn't just like sort of fun Sudoku word games to do. Like this starts to become really important when you get into hierarchical linear modeling types of things. You need to know what that 0 point is, and if you start doing that, you can start shifting things around, right? Because I want to estimate this for at this point. Well, then I just make sort of all my my predictor 0 at whatever point I'm interested in, then just measure things and then sort of get my estimator for there, right? So as you're going through, always, and I sort of said this before, we got like literally what does it mean when all my variables are held constant at 0? In this case, it means people skiing on an easy trail in the spring. My intercept indicates the odds based on our model. This is the odds of falling versus not falling on an easy trail in the spring. Okay. Does that help get people squared away with this? Okay. Think about some effect size. We got a couple different things that we can go through and do in our logistic models. You'll see pseudo R-squared statistics. These aren't true R-squared statistics. You can't interpret these as the proportion of variability in your outcome that that's attributable to the model. They're kind of generally general indices of sort of your overall quality of your model. Interpretive standpoints sort of jump around for these. A lot of times you see people argue that you don't put a whole lot of faith into these models, but they are something that will come up that you'll see. If you see someone, you read a paper where someone's reported this is a proportion of variability accounted for, tell them no, it's not. For individual predictors, you can, odds ratios in and of themselves are a direct index of effect size, right? Odds ratios, this is a meaningful interpretation, right? Particularly if we're talking about if we have categorical predictors, right? To say the odds of developing heart disease versus not developing heart disease increase are 5 times greater for smokers as compared to non-smokers, right? Like that's a meaningful sort of metric, right? So odds ratios in and of themselves can be meaningful, although you want to watch out because you can get odds ratios that are wildly statistically significant, right? So very, very small p-values, but odds ratios that are very, very small. Remember to take a look at the scaling of your predictor, right? Because if you've got a continuous predictor with a wide range, a 1 unit increase may not be much at all, but cumulatively, right, if you're taking those to powers, that's you're going to jump up really fast, right? We can also, They'll talk about this, converting our odds ratios into Ds. And this might be nice, right, if you just want to have some sort of common metric that people know and understand, right? You want to say this is a sort of large, small, medium, large effect size, taking the natural log of your odds ratio and dividing that by 1.18 will approximate a D based on stuff from Tabachik and Fidel. We can then take D, turn that into an eta squared if you like an eta squared, take your square of your D over D plus 4, you can go back and forth. And again, this is something you want to pay attention to as you move forward with your own stuff, particularly if you're going to incorporate effect sizes, sort of wanting to see general sort of translations back and forth. Generally, these are approximations, right? If you have the information to calculate an eta squared or a D, just do that instead of trying to translate the test statistic. But oftentimes, you won't have that in an article, and you'll let this give you a mechanism to go through and just try and get a general sense for the magnitude of effects. Assumptions of our logistic regression. Remember that one of the main benefits of these models is they're much less restrictive in terms of your assumptions. Your data can look really ugly. You can have weird stuff going on. And so much more forgiving in terms of having wacky stuff going on in your data that's not going to degrade the inference that you can draw from your analyses. But some things that we do need to go through and take a look at as we're looking at these models. Adequate specification, okay? Models, or sort of whatever your model is, variables that need to be in there are in there. Those that don't need to be in there aren't in there, right? And again, we don't think about this a lot. We end up saying like, oh, these are the things that I want to have in there. But you need to sort of adequately specify your model and sort of think ahead of time and sort of try and get as much as you can in there to try and make sure that you're not have something that's just crazy bonkers that isn't actually representing whatever your phenomena of interest may be. Now, we don't have any assumptions about the distribution of your variables, right? So your continuous variables can be crazy skewed. Your can have weird distributions and things along those lines. It doesn't matter technically, but note that you will have a more powerful model under conditions of multivariate normality, right? So it's not an assumption, it just optimizes your model and makes it that much more efficient, right? So these are nice models to go to if you've got like an outcome variable that's just crazy skewed, right? So, you know, 80% of your people didn't do anything that you were doing, and then some of them did, right? And so thinking about, so Katie had her proposal defense today and did a phenomenal job. But one of her outcomes that she's looking at is NSI, right? Sort of self-harm over the course of a 2-week period. That's probably going to be small base rate type of behavior, right? So if she wanted to model this as a count variable, which you wouldn't do with a normal multiple regression anyway, because you're looking at a count variable, not a continuous variable. But you probably end up with a really ugly distribution, right? Mm-hmm. So what you can do is then say, well, we're just going to dichotomize this. We're going to have people who did it, and then the people who didn't, and then just call it that. And for that, that's probably not an unreasonable way to look at those two groups of individuals running this with a regression. But then say you have maybe like a shame scale that also is really skewed, right? Because most people in my control group didn't have shame, and even the people who do self-harm aren't reporting a lot of shame. But then I got a subgroup of my people who are harming do have a lot of shame, right? So I've got a weird skewed distribution. Doesn't matter for your logistic model. It's fine. You don't have to worry about that. Now, if you have a nice distribution, it makes things just work better. You have a little bit more powerful analyses, but it's not necessary, okay? Other thing you need to be careful of making sure your outcome isn't perfectly determined by a variable or any set of variables, okay? This can get tricky, particularly if you have small samples, right? I've got 2 categorical variables and a continuous predictor and an outcome, and I've got 15 people in my sample. It may just happen that everybody in my criterion group also happens to be in sort of this predictor versus another, or some combination of those 2 things, and what you end up is a singularity within your estimation where sort of I've perfectly predicted my outcome based on just happenstance between these other 2 things. Everything will fall apart, right? This is kind of the this is the logistic version of multi-collinearity here. Generally, it's not an issue, but it can get that way if you're working with very small samples. You'll see this indicated by a failure to converge large parameter estimates with large standard errors, right? You'll get a, let's say, a odds ratio of 500. It's not statistically reliable, right? Because your standard errors through the roof suggest that there's something weird going on there, okay? Need to have sufficient representation in all of our cells, okay? What we're gonna do here is we're gonna go through, run a 2x2, not necessarily a 2x2, but run through our tables comparing our outcome variables, our categorical predictors by our outcome. What we want to have is expected frequencies greater than 1 and with less than 20% of our cells having expected frequencies less than 5. If you've done chi-square stuff and are familiar with that, so basically you need to have adequate coverage in your cells so that you're not having anybody who's actually representing sort of those different dimensions. And again, if you've got a lot of categorical variables, a lot of outcomes, you're in sort of 8-dimensional space, you can start having pretty sparsely populated cells. Want to make sure you're not having problems there. We're expecting a linear relation between your continuous predictors and the logit. Okay, so remember our logit is the natural log of the odds ratio of our target versus our not target. We're expecting that logit has a linear relation with my continuous variables, right? What we can do to test this is what we'll do is we'll take our, in our preliminary model, we'll take our continuous predictors and take the natural log of our continuous predictors, create an interaction of those 2 variables, and make sure that the interaction of our continuous predictors and the natural log of our continuous predictors aren't statistically reliable, which would suggest nonlinearity in our logit. Don't want to have outliers or huge multicollinearity, right? We don't want our continuous predictors and our categorical predictors to be correlated one with one another. We don't want to have weird outlying values. Remember, this counts for both our continuous predictors, right? We don't have a lot of assumptions, but if you got a wacky dude way out in the edge of the tail, that can still throw things way off, right? We can also have categorical outliers, right? Sort of this 9-to-1 split in our categorical stuff. But unless you've got a really large sample, you're probably going to catch that because you're not going to have anybody populating some of those cells, right? But again, one, keep an eye on that. And then independence of responses, right? Trent's data should not be related to Candace's data, should not be related to Stephanie's data. We want everything to be sort of independent of one another. But in terms of assumptions about distributions and a lot of these other things, much more lenient, much more flexible with these logistic models, and we should probably be using them more. Questions on any of these assumptions? Yes?
Linear relation, we take our continuous, we take the logit of them, we make an interaction.
No. So your logit is the log odds of your outcome, okay? And so what you will end up doing is we'll take our continuous predictor and then create a new variable that's the natural log of our continuous predictor. And then what we'll do actually, Our logistic models in SPSS are nice.